You like the transfer functions better than state space modeling? Oh, I can't believe it. Oh, it's not better, it's different. Well, if you like transfer functions or want to use the transfer function rather than state space, or you want to model it in state space and then go to the transfer function, there's actually a way to go in between them. So we're going to talk right now about how to do that. So what we do is we can start in our state space, which I've written out here, and we can transform it into the Laplace transform the same way that we would any system. So we're going to use the Laplace transformation to find the transfer function. So again, let's remember our transfer function is going to be the output, which in this case is y, over the input, which is u, based on r. So these are the states, our input's u, our output's y. So let's take the Laplace of this and see what happens. Okay, so we have one derivative, so we get s x of s, and then a x of s, b u of s. Take the transfer of the y, do it here. Y of s equals c x of s plus du of s. And in our transfer function, right, we only want it in terms of our input and output. So we really want to get rid of this x. So we can move these things around, equate these two equations together, and get rid of our x. So let's rewrite our first equation here. And we'll write it over here. So we'll move all the x's to one side. So we'll do x of s. And then this will be s. Then we're minusing a. Okay, oops, that's an a. And then over here we have b u. Okay, and we want to divide by this value, but we're working in matrices. And actually, when we do this, because we're working in matrices, it actually has to be in an IS. So we move that over, we get this expression. And when this is a matrix, because we have to have it in a matrix form. So we need to move it over. So we need to take the inverse and apply it to both sides. So to do this, we end up with the inverse of this. So IS minus A inverse, -1, then times the B and EU. Okay? Well, now we can take that and put it into this equation. So put this right here, replace it there so that we can get rid of our x. And then we'll get y of s here equals c times, well, this part. So the inverse of is minus a, -1 inverse, times b u of s. That was this whole quantity. Oops, I guess we'll close the, oh no, there's not an extra bracket there, sorry. This is the bracket here. And then this, we've substituted x in here. Now we need to add d and u of s. Okay, well we can separate out u here, and we'll actually move it straight down over here. So we'll get y of s over u of s. So we're going to take it out of both of these and then move it over. So now what's left over here is c of is minus a inverse b, we check out the u, and plus d. So these are all of our matrix values, and we can use that to find the transfer function. So this would be GP of S. And we can use, then this is our base equation. So this is a really important equation for going between the two. You don't have to derive it every time. If you just remember this equation and you have your system in this form, you can plug all these values in, calculate, and you can get the transfer function. So we'll do an example with that in a second. So I've rewritten the equation we just derived to go from the state space to the transfer function right here. And we're going to recall our favorite Valerie on a spring system. And we've already modeled it in the state space, so I'm just writing out the different components right here. And so we are going to evaluate this transfer function. Okay, so let's start by just writing everything out. So GP of S is going to be equal to C 1, 0, and then the identity times S minus A, and we're going to take the inverse of that. So we'll start by just writing this out. So it would be S minus 0, and here the lower bottom right would be S minus this value, so plus B over M. And then here we would just get negative, so we get a negative 1 here. And then a positive K over M here. Okay, and then we still have to take the inverse of this, but we will just write it like that for now. And then B will be 0, 1 over M here. And then plus D, our D is 0. So that is our expression written out. Now, the inverse is probably the least fun part of this. So let's just remember how to do an inverse real quick. So if you recall, I'll make this smaller. Okay. If we have a matrix A, B, C, and D, and we're going to call it, just not to confuse it, we're going to call it E for now, just so that it's just the expression. So E, if this is E, then the inverse of E is going to be 1 over the determinant of E, take the determinant of this matrix, times, and you have to flip these two, so it's D and A here, and then take the negatives of these. So negative C, negative B. Okay, so not the most fun, but let's take the determinant of E, so the determinant of this matrix here. So we'll keep everything in its form. So here we still have 0, 1. Now we're taking the determinant of this, so 1 over that. And so it would be S times S plus B over M. This times this minus this times this. So it would be a plus K over M. So there's our 1 over the determinant. Now we need to just flip these things around. So swap these two. So we get S plus B over M here. And then S in the bottom right. And then take the negatives of these. So negative K over M. And then positive 1. Okay, so there's our inverse. And we still multiply that by 1 over, and then 1 over M here. Sorry, 0, 1 over M. And then we don't have to add in the 0. So now we're here. Now we need to evaluate this. So let's start from the right. So let's look at multiplying these two matrices together. Remember, this is a scalar, so we can leave it kind of in the middle here. And we're going to multiply this out. Let's rewrite everything. And we're going to actually shorten this a little bit. 1 over S squared plus B over M, S plus K over M. Okay, and so if we multiply this out, we'll get 0 plus 1 over M in the first spot, 1 over M. And then 0 plus S over M. Okay. Okay. So we're getting closer. And this again is our scalar, so we can actually move it out to the front and we can do the multiplication of these two matrices. So 1 plus M times 0 plus, we'll write it out. 1 over S squared plus B over M, S plus K over M. This is our scalar out in front, so now let's multiply these two matrices and we'll get 1 over M plus 0. Okay, so now we have a scalar here. We can multiply this all out. Why don't we actually move the M to the bottom? And we will get GP of S. So the transfer function is equal to 1 over, so M times S squared plus m times b over m, so b s, multiply the m, so plus k. And this should be equal to our transfer function. If we go back and check the original transfer function that we did, we'll see that they are the same. So this was successful in our transformation. Probably the most unfun part about doing this transformation is doing this inverse. If you get a very large A matrix, it's best to use MATLAB rather than trying to do it by hand. But with this one, 2 by 2, it's usually not too bad. So we're able to take the state space. If you don't like state space for some reason and you want the transfer function, then you can transform it using this equation.